One of the key principles in calculus is that a differentiable function is locally linear, which means that if you zoom in close enough, it starts behaving like a line. And what that also means is that the tangent line is a really good approximator of the function as long as you're really zoomed in, as long as you're really close. Obviously, the farther away you get from the point of tangency, the worse the tangent line does. So in this section, we're going to actually look at the tangent line, and we're going to kind of start to use it to help us approximate the values of the function. So just a note on the tangent line, and then we'll turn it into what we want to use it for. So the equation of the tangent line is usually given in point slope form, right? So you usually start with this form, where m is the slope and x1, x1, y1 is a particular point. So we're just going to change up the notation a little bit here, and I'm going to solve for y, so I'm going to add y1 to both sides. Oops. And then I'm going to go replace some of this generic algebra notation with calculus notation. So, for instance, y1, well, that's just the point of tangency, right? It's the y value of the point of tangency. In calculus, since we're going to use function notation, that would be f of a. So this point right here is x1, y1, but in calculus notation using functions, we would call it a comma f of a. So I'm going to replace this with f of a. The slope of the tangent line, well, that's just the derivative at a in this case. So I'm going to call it f prime of a. And then my x1 is just the value a. So I haven't done anything really sophisticated here. I've just changed some notation, some labels, some symbols. Now, I can't call this f of x because f of x is the function itself, but I do want to view the tangent line as a function, so I'm going to call it L of x. All right, and so that is what we call the local linearization of f at a. All right, and again, this only works if your function is differentiable at a. But if that's the case, then an important thing to point out is that, and I'll give you an example on the next slide, it's that the function f of x is really close to L of x, near x equals a. Right? If you're really close to x equals a, then the curve and the tangent line are behaving the same way, and they're one can probably be replaced with the other in terms of computation. And lines are usually easier to compute with, so we probably, when we can get away with it, we use lines. So for terminology, another thing you might hear is that this is called the standard linear approximation of f at x equals a, and x equals a is often called the center of approximation. So this word approximation is used because, again, the linearization or tangent line can be used to approximate the function for values really close to a. So on the next slide, let me just give you a particular example so you can see how good of a job that the linearization does at approximating a curve near the center of approximation. Alright, so here I've got square root of x and the linear approximation to f of x at the point 1, 1. And so obviously the black is the tangent line. And the point I want to make is if you zoom in, you can start seeing that they become pretty much indistinguishable. Right? And I mean, at this point, you can't even distinguish them. They will always be the same at the point 1, 1. But for values, I'm just going to put some values in close to 1. If I put in like 1.1, for instance, into the line, and I put in 1.1 into the actual function, you should compare the values. So there's, see if I can get this up here. Yeah. So the actual value of the function at 1.1 is 1.0488, and the value of the linearization at 1.1 is 1.05. So very, very close. And clearly the closer you get to 1, the better, or the closer these approximations will be.